Hello, welcome to CE5361 Engineering Hydrology, Lesson 21, Probability Estimation Modeling. This lesson reviews some of the fundamental concepts in probability estimation modeling, in particular how it applies to our work as hydrologists. Much of the material will probably be review for students attending the course. Treat it as such. It's a review. I have expectations that you can do much of the manipulations that are described herein. Some important readings are Chapter 13, the entire chapter, Elements of Frequency Analysis and Hydrology in the Kindle edition textbook, and also pages 350 to 380 in Chow, Maidment, and Mays. And this is a link right here, so if you go to the course content or the course lesson pages, you should be able to link directly to that document. It's on the server. We'll go verify that in a second. And also FHWA NHI 02-001, McEwen, Johnson, and Reagan, Highway Hydrology section or pages 4-1 through 4-41 are applicable. The Texas Hydraulic Design Manual, I think it's actually Texas Hydraulic Manual. This link is to the 2014 edition. By now being 2020, there's some substantial, not content changes, but the layout is changed. It's all online. And in the 2014 manual, pages 4-13 through 4-30 are relevant. And finally, some 2006 notes on probability estimation modeling from a class called CE5361 taught at the University of Houston by myself, summarizes the ideas here. So these readings would be good to do beforehand, but obviously if you're watching the video, you're going to do it afterhand, and that's fine. So what is probability estimation? Or how's it all important? What it is the use of probability distributions to model or explain behavior and observed data. Now, the reason that's important is once we've selected a distribution of some kind, then we can look at the concepts of risk for events of different magnitudes. Alternatively, we can determine the probability of observing an event of a given magnitude or greater, and that's called exceedance probability. So the concept of risk, which is a code word for probability, can be explored for things like rainfalls, discharges, concentrations, intensity, duration, frequency, and so forth. So there's two important extremes in civil and environmental engineering, at least relevant to this course, which are relatively uncommon or rare events: floods, plant explosions, nuclear power plant meltdowns, global virus infections, to very common events, routine discharges, or what is the discharge in the stream that can be expected 90% of the time, which would have relevance in wastewater engineering. If we were going to choose to discharge treated water into a receiving stream, we want the receiving stream to already have enough flow in it so that our contribution from our wastewater plant is not hydraulically substantial, which could cause erosion and other things, or pollutant load substantial, which could destroy the water quality of the stream from that point downstream. We won't focus that much on water quality in this class, but that's the other use, or the use of common events. So first we'll discuss frequency analysis, and then in a subsequent lesson we'll discuss something called a flow duration curve, which is very much like an intensity, duration, frequency curve for rainfall, but it has to do with stream flow. So frequency analysis relates the behavior of some variable over some recurring time intervals. And the time interval is assumed to be large enough so that the concept of frequency makes sense. And the concept of long enough is required for statistical independence. That is, the values of the variable are statistically independent. Otherwise, the variables are said to be serial correlated, and you could certainly apply the techniques of frequency analysis, but the results would be maybe not meaningless, but not as useful as they could be. Serial correlations are somewhat hard to deal with. Not impossible, but you have to know it's serially correlated and apply appropriate tools for that. If the time intervals are short, hours, days, weeks, that's probably a time series, and they're handled using entirely different toolkits. The T-year event is a concept that occurs frequently in hydrology, and it's a way of relating chance or probability. It's called an annual recurrence interval, and it's the probability of observing an event of some specified magnitude or smaller, some specified magnitude or larger, depending on whether it's a non-exceedance or an exceedance probability statement in one sampling period. In the case of the T-year event, that sampling interval is a 1 year, either a water year or a calendar year, usually a water year. And I think it says here it's also called the annual recurrence interval. The formal definition is the T-year event is an event of magnitude over a long time averaging period whose average arrival time between events of such magnitude is T years. So the arithmetic involved, something with an x-year annual recurrence interval is equal to 1 year divided by the x-year, or 1 over x annual exceedance probability. So for example, a 100-year annual recurrence interval is equal to 1 over 100, which is 0.01 annual exceedance probability, or the 1% annual exceedance probability is probabilistically the same as the 100-year annual recurrence interval. The annual exceedance probability is clearly a related concept, and generally it's the preferred way of stating the probabilities. Typical notation is something like this: the probability of observing something lowercase x being greater than capital X has a value of equal to y, where y is the probability. We read them: the probability that random variable x will assume a value greater than cap x is equal to y. That's all that notation means. One use is to generate flood frequency curves, which we'll spend some time in a little bit. So here is a flood frequency curve graphic lifted from the Texas Hydraulic Design Manual, and the purpose of this one is to illustrate some parts of the curve. So we've identified the 50th percentile, or the mean event. So the cursor should be moving up and down on the video, making you nauseous. And we're at annual exceedance probability of 0.5, which would be a 2-year annual recurrence interval. And if we stay on that probability line and go up into the intersection of the flood frequency curve and the probability line, and then move left, we return a stream flow value, in the case of this particular curve, of 20,000 cubic feet per second. And the way to interpret that drawing is that the probability of observing 20,000 cubic feet per second or greater in any given year is 50%, or 0.5, or a 2-year annual recurrence interval. So this corner, which is shown in the rose color, is the non-exceedance probability. So there's a 50% chance that the value won't get bigger than 20,000. And in this corner up here in the blue, there's a 50% chance that the flow will be 20,000 or greater. This is called an exceedance probability. They're the complement of each other. So if you know one, you know the other. Another way to use the tool would be what is the probability or annual exceedance probability of observing an event of specified magnitude or greater in any year. So we would go to the magnitude. So here we have about 150,000 CFS. We move horizontally until we intersect the flood frequency curve, and then we would read down to the probability, which here is shown as 0.010, or that'd be 1% chance of observing 150,000 CFS or greater. So it's referring to this blue region up here. There's a 99% chance that we will see flows larger than 0 and smaller than 150,000 CFS. So that's what a flood frequency curve conveys. And it doesn't necessarily have to be floods. It could be water quality. It could be average flow rate over a 7-day period. There's a lot of different random variables that can be examined in this fashion. So next we want to consider what probability models are. So the probability in a single sampling interval is useful in its own sense, but we're often interested in the probability of occurrence over many sampling periods. If the individual sampling events are independent, then the they're identically, let me repeat that. If the individual sampling interval events are independent and identically distributed, then we satisfy the requirements of a Bernoulli process. And as a simple example, let's assume that the probability that we observe a cumulative daily rainfall depth equal to or greater than a tropical storm Allison is 10%. So Tropical Storm Allison was a storm in the Gulf Coast in 2001. It was just before September 11th. So it was late August or mid-August, and essentially this tropical storm, the tropical depression, parked over the Houston-Galveston area for 3 days, and it caused substantial flooding, property damage, and loss of life. Later on, Hurricane Harvey came by, which became, I believe, an event of record. But up until that point, Tropical Storm Allison was one of the rarer or higher magnitude events that had occurred in the area. So there's some background. Let's assume that seeing that happen is 10% in any year. So we might want to ask ourselves, what's the chance we would observe one or more Tropical Storm Allisons in a 3-year sequence? So let's state that we have 3 years, year 1, year 2, year 3. And year 1, there is or is not a storm big enough. Year 2, there is or is not a storm big enough. Year 3, there is or is not a storm big enough. Now we want to know what the chance is of one or more, which is the same because it's a mutually exclusive. It's the complement of observing none in the 3-year period. So no Tropical Storm Allison year 1, no year 2, no year 3. This is a small problem, so we can enumerate all the possible outcomes. So one outcome of that 3-year series is no storm, no storm, no storm. The second outcome is no storm, no storm, storm in year 3, no storm, storm in year 2, no storm, storm in year 1, no storm, no storm, and so on. No storm, 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 no storm, storm, no storm, 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 storm. So the probability we're interested in is this first row. Since these are independent, identically distributed, the probability over this 3-year sequence is simply the product of each of the probabilities, 0.9, 0.9, 0.9, 0.9 cubed, which is 0.729 or 72%. So we have a 72%, well, actually 73% chance of seeing no storms in a 3-year interval. And so 1 minus 72% or 73 is 17. So we would have a 17% chance of observing one or more storms. And so these numbers remaining should add up to 0.17. So if we're concerned with a single storm in the next 3 years, the probability of that outcome is 0.243. So its outcome 2, 3, and 4 would satisfy exactly one storm. 2, 3, and 4 are exactly one storm events. They have a probability of 0.8081 each, and you would sum those 3 up because they're mutually exclusive. The probability of 3 good years we've already seen is 73%. The probability of good outcomes, or as we've defined good, it's going to decrease as the number of sampling intervals are increased. So we already seen 3 years it's 73%, but if we go for 10 years, the chance of no storm is 35%. If we go 20 years, it's 12%. If we go 50 years, it's 0.5%. So over 50 years, you're almost assured of seeing a storm. So as the sampling intervals increase, the the collective probability decreases. Fancy way of saying if you wait long enough, something's going to happen. So one probability model is at some point there's too many possibilities to conveniently enumerate. We can't build tables like that. And in that case, if we're trying to find the chance of observing case storms in n sampling intervals, we can use the binomial distribution. And here we have the probability of k events occurring in n samples, and if the probability of an event in any single sample is p sub t, then the net probability is n factorial divided by n minus k factorial times k factorial times the probability of the event in a single interval raised to the kth power multiplied by the complement of that probability, 1 minus p sub t raised to the n minus k power. Now this particular distribution enumerates all outcomes assuming unordered sampling, so the order of arrival doesn't matter, and without replacement, meaning once a sample has been drawn, it's not put back into the hopper. There's several other kinds of counting. 3 of them are listed here: ordered with replacement, where the order matters. This is somewhat important in the L moment method. And the samples are replaced, unordered with replacement, and ordered without replacement, which I think is how the L moment thing is dealt with. Once we have probabilities, we can evaluate risk. So insurance companies use these principles to determine premiums. We'll take a brief tangent here. In the case of insurance, one can usually estimate the dollar value of a payout, or actually there's a policy. You agree to what that's going to be. Let's say it's $1 million. And then the actuary calculates the probability of actually having to make the payout in any single year. Let's say it's 10% chance. We can use the same table. The product of the payout and the probability is called the expected loss. It's a dollar value. It's the expected loss, but it's a risk-weighted concept. The insurance company, if they want to make profit or at least stay in business, would charge at least enough in premiums to cover the expected loss. So the expected loss is not the same as the payout. Because there's only a 10% chance of making that payout, the expected loss is $1/10,000,000, be $100,000. Then they determine how many identical independent risks they have to cover to make a profit. So we don't sell a single insurance policy. We have to snooker a whole bunch of people into buying that same policy. And it's the basic concept behind flood insurance. If there's enough people in the risk base, the probability of all of them having a simultaneous loss is very small. And so the losses that do occur can be covered plus some profit. If we were to use the above table, so let the years now represent different customers, the probability of having to make one or more payouts is 27%. So here we have customers 1, 2, and 3, and for us as the insurance company, the most desirable outcome is nobody incurs a loss. We have a 73% chance of that happening. We have one loss, we pay out $81,000. We have a different customer, $81,000, a different customer, $81,000. We have customer 2 and 3 incurring a loss. We pay out $9,000. Excuse me, not pay out. Our expected loss is $9,000. So what it is it's the probability multiplied by the payout. And so the insurance company's net expected loss, which is the sum of these columns, is $271,000. And so if we charge each customer $100,000 for a $1 million policy, we're going to take in $300,000, which is more than our expected loss. and thus it's $29,000 more than our expected loss. So we have a 70% chance of producing $29,000 of profit. And actually we would produce more than that, because if we get the 70% chance, we don't actually have we don't incur an actual loss. And so we take in $300,000, we pay out zero. Now there is a chance that we'd have to make 3 payouts, and that would be $3 million, which would be problematic. And so to prevent that from happening, we would either charge enough in premiums to assure that there'd be no loss, increase the customer base, and or misstate the actual risk. So that last thing is illegal. But if we don't know how to calculate the risk, then we're not really breaking a law. So that's the idea of risk, in this case in an insurance context. So the insurance company's gamble is that on average they're only going to lose $271,000, but they're going to take in $300,000. Worst case, they're going to lose $3 million. Best case, they're going to lose nothing and pocket the $300,000. And so if you have enough customers, the arithmetic works out pretty good for you. So that's the idea of risk. Some of the data is needed for making probability estimates from a hydrologic context. It'd be most desirable to have a long record of the variable interest at the location of interest. If that's the case, we might even be able to use just empirical frequency distributions. Build directly off the observation set. No statistics involved, although that would never get done. A long record of the variable near the location of interest. Third most desirable would be a short record of the variable at the location of interest. Fourth would be short record near the variable of interest. And fifth would be no records near the location of interest. Case 5 is by far the least desirable, hence it's the most common. But we're going to look at some of these other ones. What we have is methods to infer what the likely behavior is at the location of interest based on nearby information. And in this case, nearby might be quite a long distance away. It might be something that's regionalized, so we may have nothing nearby, but we have a state of Texas probability estimate, and that would be how that would get used. So frequency analysis is used to produce estimates of T-year discharges for regulatory or floodplain delineation, T-year 7-day discharges for water supply, waste load, pollutant severity determination. There's other averaging intervals other than 7 days are used, and that's gets into the flow duration world. T-year depth duration frequency or intensity duration frequency for design storms. Storms that are to be put into a rainfall runoff model to estimate storm cause peak discharges and so on. So observation data are fit to some distribution, and then the result of that fitted distribution is used to extrapolate behavior. So consider this example here, and we're actually going to examine these in more detail shortly. So the blue markers represent observations. And imagine, if you will, that we have, I guess, 27 years of record of annual peak discharges. And then what we want to do is fit a probability distribution to it. In the case shown here, this black line is the normal distribution passed through the data. It's not a very good fit, but that's beside the point. And we now have a cumulative density function, which has a quantile, which is a probability. Think of that, a magnitude, and the probability of that magnitude is equal to 1/2 1 plus the complementary error function of x minus mu over 2 sigma. So for a given magnitude, we can recover an x, although that's not usually how it's done if you're doing it by hand, or for a given magnitude, we can recover a probability. So we use the blue dots to fit the black curve, and then we make our probabilistic inferences based on the black curve. So if this was indeed the chosen probability distribution for these data, the probability of observing a 3,100 cubic feet per second event is 090807, 0.07, so 7% chance of seeing that value or greater, 93% chance of seeing 3,100 or less, according to these data. There's several distributions in use. We're going to go through a few of them here, and we'll see examples of these in a minute. One is the normal distribution, and the important metrics of the normal distribution are the mean, mu, and the standard deviation, sigma. A gamma density function, which is a different probability function. Here's the cumulative density function for the gamma distribution. The unknown parameters are lambda and n. N does not have to be integer, although if it is integer, gamma of n is n factorial. The extreme value Gumbel distribution, this is called the double exponential distribution. There's several different Gumbel distributions. I think this is called an EV type 2. And there's one more I don't have listed, which is log Pearson type 3, which is commonly used in the United States. So we have distribution model. The next is how those blue dots get plotted, because it's somewhat suspicious that they're plotted on a probability axis when the data are actually associated with a particular year. And the way it's done is use something called a plotting position. And a plotting position formula estimates the probability value associated with specific observations of a stochastic sample set based solely on their respective positions within the ranked or ordered sample set. So in this case, I is the rank of an observation and n is the number of observations. There's one not shown here, which would simply be I divided by n, which would be the relative frequency. But the Weibull distribution is common, and that's actually what appears in Bulletin 17B, which has since been superseded with Bulletin 17C. And the formula is the rank divided by n plus 1. There's a Blom, which is I minus 0.375 divided by n plus 0.025. Cunnane plotting position, Green-Gorton, Hazen. There's a few more. And so what's changing around here? So this value A is what's going in this location here. And then the weights are adjusted depending on the various author. And so what these are trying to do is provide a empirical representation of cumulative frequency based on the observations. Now, if you have, the more observations you have, if these are annual, the better job the plotting position is going to do, because for one thing, each of the weights associated with any individual observation is much smaller, and you're compensating for that by having a lot more observations. For example, if you wanted to compute the 1% chance event, if you had 100 observations, then each observation represents 1% of the total, and so the largest number in the observation set would be a good estimate of the 1% chance observation. So with plotting position formulas, the values are assigned based solely on the set size and the observation position. The magnitude of the observation itself has no bearing on the position other than to generate its rank. So Weibul's in common use, Cunnane is general use, the Blom is optimal for the normal distribution, and the Green-Gorton is optimal for the Gumbel distribution. To produce plotting positions, we rank data from small to large magnitude. If we do it from small to big, we're producing non-exceedance probability rankings. If we do it from big to small, we're producing exceedance. Again, they're the complement of one another. Compute the plotting position according to selected formula, P, or the position, is the relative frequency associated with that observation. Plot the observations on probability paper, and in the olden days, based on how those plots fell on probability paper, you can infer behavior of the population. We're going to use the Beargrass Creek example right now. We're going to just go through pictures, but we're going to do it live in a minute. So suppose we have this set of observations right here, discharge and years. We can rank those from small to big, compute the Weibull plotting position according to the Weibull formula, and now we have these three columns: rank, discharge, Weibull plotting position. The year is now, it's technically lost, although you can carry along the year for other purposes. Then we write the ranks, apply the plotting position formula, and build a cumulative density plot. So here we have empirical cumulative probability, and the circles represent the individual observations. And the way we can look at that is the smallest observation we have is 707. So the probability of observing a value of 707 or less is, looks like about 3%. The probability of observing 707 or more is 97%. So the exceedance probability, the probability of seeing 707 or more, is 97%. As we move up in the magnitude direction, we're moving over here on the probability axis. Let's go to this last one, 5,200 in the cumulative. In the empirical, the probability of seeing 5,200 or more is 4%. Probability of seeing 5,200 or less is 96%, based on its position in the plotting position. So at this point, all we can do is evaluate the empirical cumulative density function and infer probability and magnitudes within the observation range. So we can do interpolation. But the next step is to fit a probability distribution, and that allows us to extrapolate. So that allows us to estimate the probability associated with values greatly beyond this 5,200, up here in the 10,000 range. So some examples are normal, Gumbel, and log normal. Here's a normal distribution fit by conventional method of moments. So we calculate the mean and standard deviation, and that gives us the information to fit a normal distribution. Here it is plotted. We're going to look at an R script that does the same thing. Gumbel distribution, also by method of moments, using a formula for estimating the alpha and beta of the Gumbel distribution. Once we fit the distribution, then the distribution parameters are used to estimate magnitudes for arbitrary probabilities, or actually the other way around. You specify a value and you see what the probability is, and then you trial and error that to get what you want. So, for example, if we want to estimate the 20-year annual recurrence interval, let's, I think it's, doesn't matter. 20 years is 50%, 5%. So it's about right there. 20 years should be about 1,800. Ooh, I'm wrong. So we do 1 over 20, which is 5%. So we want to find the value that makes the CDF equal to 0.95, which is up in here. And the value that makes that true is 2,590, depending on which probability model we've used. And the end statement would be that the 20-year annual recurrence interval of this particular stream is 2,590 CFS. If we do it for the 100-year or the 1%, we estimate the probability. We want to find the value that makes the CDF equal to 0.99, and in this case that's 3346. And we'll check those out in a minute. The next distribution is log normal. In this case, log normal actually has a pretty good fit, seems like. And the log normal is we fit the logs of the observations. And so the mean is the log mean and the log standard deviation, and that produces the red line here, which passes nicely through the observations. Once fit, we can use the distribution parameters to estimate the probabilities of specified discharges. 3,200 is 95%, and that is how probability estimation modeling is done. So a quick review of the workflow: rank observations, compute plotting positions, plot the empirical cumulative position, this distribution. Now that's optional, but it's important to do that to check that the end result makes sense, to see that those curves and the dots are in the right place. Then we would select a probability model or use one selected for us, fit the model by a variety of methods: method of moments, maximum likelihood estimation, expected moments analysis, L moments, which is a ranking scheme, and so on. If we're really advanced, we'll check for outliers. Some of those observations may not fit the rest of the data very well. And then use the model to infer magnitudes at desired cumulative probabilities. So that's the essence of probability estimation modeling. Let's now look at some examples. Here's our shared space, and I've moved the Beargrass Creek data up to the server. Using the Moodle site. So let me go ahead and get that up and running. Now I need to do it on my local machine because I actually hadn't moved the data yet. Mr. Bond's private files. And I want to actually move all of those. Hope this works. Yay, that's kind of reassuring. Save the changes. Back to here, it should be there. Excellent. Now, see if I can resize things a little bit. We're going to download those. All right. I think I've got all of them. It'll tell me. All right, now let's see if we can find the downloads. It should be in Home. Downloads. Gamma, Gumball, Gumball 2, Log Normal, Normal. Okay, I think that's all we need. I'm going to move these to the desktop. Okay, so this will illustrate our probability estimation modeling. Let's first take a look at the input file. And so it has year and Q peak and CFS, and it's from 1945 to 75, and these are the different values. And get our studio running. We'll start with normal distribution is as good as any. Actually, yeah, we'll just do the normal. Okay. So here is a script to do the normal distribution. It's a typical R script, and we'll just briefly look at the contents and then run it. So we have some prototype functions. The first is the Weibull plotting position, and it would be easy enough to use a different plotting position formula if you wanted to. And in this case, it takes input X, it sorts it, and then produces the denominator, which is the length plus 1, the n plus 1, and then it ranks it. And then the ties method is the first available breaks the tie. And then we sort the result of ranks divided by denominator and then return the result. Okay, the next prototype function is the normal cumulative density function. Turns out normal is built in, and the function is p norm, and it takes an argument as x, mu, and sigma. We set lower tail to be true, and that gives us a accumulation from negative infinity to the point of interest, and then we'll return that value. And now we'll read the file. Q of db beargrass.txt. Got some labels here, and then we'll compute the mean and the standard deviation, and I'll make up some invented discharges from 700 to 9,000 steps of 100, and that's for plotting. And then we'll actually get the associated probabilities with this sequence of 700, 9,000 steps of 1,000 from the normal CDF, and then we'll plot our model, and we'll plot the plotting position versus the observations, and this will give us a way to see how good we do. So let's go ahead and actually going to run this in pieces. And we could check that if we wanted to. We could plot q.db. I believe the first variable is called q, is year. The second variable is q.database qpeak. Oh, my bad. I have to set the working directory to the correct place. Now let's plot. So here we have the observations, and if we're to look at this, see the horizontal axis is year, vertical is discharge. The average is, somewhere a little below 2,000, and we have these three relatively high ones here, and then most of the remainder are between 2,200 and 700. And that's about all we can get from the initial observation set. If we wanted to get fancy, we do that, which isn't very helpful. So there's not a lot to be learned just from the data. But now what we can do is we'll go ahead and fit a normal distribution and see how that works. So I just fit the normal distribution, and now we're going to plot the observations with the Weibull plotting positions and the fitted normal distribution on the same axis. And so here's our normal distribution fit. Not horrible. Kind of loses it up here on the right edge and is pretty bad at the low flows. And I would think that the whole thing would want to be shifted differently. We'll just leave it be for the time being. And so let's suppose the blue line is our probability estimation model. We've decided that's what we're going to make our decisions on. Let's now go ahead and there we go. It didn't read in this prototype function correctly. So now we're going to enter a value for discharge. And let's quickly go back to the presentation and see what value worth checking. That's log normal. That's Gumbel. Oh, we don't have much with so I think the Gumbel distribution 3346 was the 100-year ARI. We'll just see what that does in this case. I don't expect it to be the same because it's a different distribution. So the estimated exceedance probability is 4%, or non-exceedance is 96%. That's pretty close, actually. So this is saying that there's a 4% chance of observing a value of 3346 or greater. So that's how probability estimation modeling is done. That was for the normal distribution. Let's go ahead and look at a few others, since somebody has gone to the trouble to program them already. And the programs are all identical, except for the underlying distribution. We'll do log normal. Open that. So log normal, I think, is the best fit for these data. And we do have an example to compare to. We have a, see, that was log normal. We have a 20-year magnitude of 3200 should produce 95th percentile. We can check that real quick. 3200. 4.99. So 1 minus 4.99 is 95 and some change. So this result and this result are, for all practical purposes, identical. We have two more, the Gumbel and the Gamma. So let's go ahead and look at the Gumbel example. So there's our Gumbel distribution. The pictures all look quite similar. Now, it makes sense that the dots look similar. It's the same dots, but the curves all look similar, namely because I'm plotting on a logarithmic axis here and a probability axis there. There's some mapping here that goes on, and let's see, we had a 100-year Gumbel of 3346. So it should produce a result of somewhere around 1%, 0.96%. I'd call that somewhere around 1%. And the last one we can try is Gamma. Now the Gamma is a is deceptive for these data. It's not a very good distribution for explaining these data, but it could be used. And I want to see what we'll use 3346 for that. And so that's at the 94 percentile non-exceedance or 6 percentile exceedance. So assuming if the gamma distribution is what we think is the model of the data, then the discharge of 3346 CFS would be expected 6% of the time to see 3346 CFS or greater. And that's the essence of probability estimation modeling. Now the one distribution left off is the log Pearson type 3, which will be left as homework or for future work. And I can now, hopefully that's our studio I'm killing, yep. So now we've just run through these distributions. We don't need the gumball. See if I can delete it. Ta-ta, bye-bye. There we go, and I will leave that in HYDRO1 in the HydroShare environment. And you'll have the password for that, so you can log in and check it yourself if you need to. And let's disconnect from the remote. And the content repository contains the lesson 21. And the video is stored on the YouTube site, and that link is contained in the lesson. So thank you very much for your attention, and that concludes lesson 21, probability estimation modeling.